Hello guys, in this video I want to show a really important example of subset X of a plane R2 such that X is not going to be a manifold. However, it might look like a manifold, but it's not. So I'm going to take X to be the union of X-axis and Y-axis. So if we have a plane R2, then my X is going to be just the union of these two lines. Okay, so let's show actually that X is not a manifold by using the definition that I gave you in previous video. What does it mean to be a manifold? So I'm saying that X is a manifold if X is locally Euclidean. So let me elaborate a little bit more on this concept locally Euclidean, and let me show you a different perspective. The idea is if I have my X, then I can choose any point P in my X, and for this point P I can find a neighborhood in the following way, that if I'm going to zoom in towards my point P, then this neighborhood either going to look like a real line R1, or it's going to look like a plane R2, or an Euclidean space R3, and etc. And the idea is that we have a natural coordinate system on my Euclidean space, which is Cartesian coordinate system, that for every point I have a coordinate, for example, like 1, 1, and 0, and then in some sense I can leave this coordinate system upstairs over here, so I'm going to have a coordinate system on my manifold. So, in order to detect that some X is not a manifold, I just need to find at least one point for which any neighborhood is not going to look like a real line, a plane, or any Euclidean space Rn. So for example, if I'm going to take any point, let's say P1 or P2 on X or Y axis, then we can see for this point I have a really nice neighborhood, which is an open interval. And open interval, if I'm going to zoom in, then it's going to look like a real line. But if I'm going to take this point P, which is exactly the origin, and you can see every time when I'm going to take some neighborhood, like open ball, it always going, and if I'm going to zoom in towards my origin, I'm going to have the following picture, that it's always going to look like this intersection. And right now, if I'm going to take this intersection of these two lines, and I'm going to compare this intersection to any Rn, then you can see that this intersection is not similar to any of Rn. And being similar, I'm going to discuss in my next video, which means just be homeomorphic. But let me actually show you that they not the same, or in other words, not homeomorphic, by using just geometric intuition. So if I'm going to choose this point P over here, then I'm going to get the corresponding point P on for some Rn. So it's either lines, plane, or space. But if I'm saying that the neighborhood around point P is not distinguishable locally from some Rn, then it means if I'm going to throw away this point, then the complement of this point is also going to be non-distinguishable. And one really important property of being homeomorphic, that it preserves the number of path-connected components. So what is the number of path-connected components? It basically means that for any 2 points in your path-connected component X and Y, you always can find a path. And here you can see that if I'm going to throw away this point P, then I'm going to have 1, 2, 3, and 4 path-connected components, because literally my neighborhood without the origin is going to look like this. So if I will choose any point X and Y here, there is no way how can I find the path within the X-axis and Y-axis. But if I'm going to throw away a point over here, then here you can see that you're going to have only 2 path-connected components, since your real line is going to look something like this. For the plane, if you're going to throw away this point, you're going to have only 1 path-connected component, because your plane is going to look a plane just without a point. And the same works for a space. If I'm going to take my F3 without a point, then you can see that every time I'm going to choose any point X and Y, I always can find the path. So X is not a manifold, because for this point P, for any neighborhood, if I'm going to throw away the point P, the structure of the complement is going to be completely different than the structure of the complement for any Euclidean space. That's why X is not a manifold. Okay guys, thank you for watching. Let me know if you have any questions. If you're not subscribed to my channel, please subscribe. Bye bye.